Okay, this is Unit 9, Video 1 on simple harmonic motion and sound, and waves, sorry. Alright, so today we're going to describe simple harmonic motion in terms of force, motion, frequency, amplitude. We're going to solve for a period of pendulums. We're going to differentiate between types of waves, and we're going to solve for frequency, wavelength, and wave speed using wave equations. So to start, we're going to just talk about periodic motion. It's a motion that repeats itself in equal intervals of time. It's called harmonic motion. Okay, so any motion that repeats itself in equal amounts of time is called harmonic motion. When an object moves back and forth over the same path in harmonic motion, it is said to be oscillating. Okay, and if the amount of motion of an oscillating object stays the same during the period of motion, it's called simple harmonic motion. So the distance that the object travels stays the same, then it's called simple harmonic motion. So examples would be like the pendulum of a clock, right? That's simple harmonic motion. It's the same amount of time, it's the same motion, it covers the same distance every time. Okay? So the first example we're going to talk about is a spring mass system. So this would be like if you had like a cart, and you had like a spring over here, and maybe a spring over here, and we're basically going to identify max and minimum values of displacement, velocity, and acceleration. So these graphs are going to be, this is going to be a D versus T. I want you to write the letters kind of far away from the graph. This is going to be a V versus T, and then this is going to be A or F versus T. Okay, so force or acceleration. Same, it'll be the same graph. Then we're going to do a positive and a negative on each graph. Okay, and we're going to identify the motion of this cart. So we're going to go ahead and say that the cart starts to the far right. Okay, pushed up against this spring. All right, so, and down below here we're going to say right origin, left origin, right. Okay, so right origin, left origin, right. Same thing, right origin, left origin, right. Okay, and so we're going to kind of graph what is the displacement at these different positions. So when it's far right, okay, so when it's far right, its displacement is positive, right? So from the origin, which is the center, okay, if the cart is pushed up against to the right, then it would have positive displacement from the origin, okay? At the origin, its displacement would be 0, okay, and actually you can fill that in for both, right? At the left, its displacement would be negative, or as far negative as we can get. And then when it goes back to the right again, it'll be positive again. So this graph would look something like that. Okay? Now the velocity. When it's pushed all the way to the right, it should have a velocity of 0. Okay? At the origin, it should be at its highest velocity, but when it's coming from the right, going toward the left, which is what's happening at this origin, going from right to left, it would be negative. It's maximum negative. Then when it's all the way at the left, it has a velocity of 0 again. You can imagine it would stop, right? And then on its way from left to right, so now it's moving back toward the right, and it passes by the origin, it would have the highest velocity in the positive direction. And then when it makes it back to the right, we'd be back at 0 again. So this graph would look something like that. Okay. Last piece, the acceleration and the force. And this one's a little bit hard to picture, but so when we're far right, the force of the spring pushing on the cart is to the left, and it's at its maximum force when it's pushed all the way to the right. So maximum force pushing to the left would give us a maximum negative force. Okay. Then at the origin, it should have 0 force on it. Okay. And 0 acceleration. When it is pushed far left, the force would be to the right at its greatest amount. Okay. Back to 0 when it hits the origin. It's still moving, but it's just not being pushed or accelerated. And then when it's far right, it'd be back to the negative. So this graph looks something like that. Okay. All right, let's talk about pendulums. Okay. The equation for a period of a pendulum, and it's going to be maybe surprising a little bit, but the period for a pendulum really depends on length of the pendulum and gravity. So for Earth, G is negative 9.8. And actually, in this equation, we're not going to put negative because you can't have a negative under a square root. So you'll just use the positive. Okay? So let's do a quick example. What is the period of a pendulum on Earth with a length of 1? So L is 1. They should be in meters. Earth means that G is 9.8. Okay, so the period of a pendulum would be 2 pi square root of 1 over 9.8. All right, and let's go ahead. It'll come out in seconds because of this. So we have 2 times pi square root of 1 divided by 9.8. And we get about 2 seconds. Now, what would the period on the moon, where gravity is 1/6 that of Earth? So now, the thing that changes is this is actually 9.8 divided by 6. So it's 1/6 that. So 9.8 divided by 6 is 1.63. 1 divided by that, and then square root, and then times 2 times pi. You get a period of about 4.9. Oops, dyslexia there. 4.92 seconds. So when gravity is lower, the period actually goes up because it takes longer. You can imagine a clock here on Earth, it does this, right, every 1 second. But on the moon, it takes longer for gravity to pull down. So it's going to be going slower. So it's going to take longer for that one period. Okay. All right. Resonance. There's a lot of vocabulary in this section. Resonance occurs when forces are applied to a vibrating or oscillating object at time intervals equal to the period of oscillation. As a result, the amplitude of the vibration increases. This is, we're going to talk about some examples, but resonance is like when you're pushing a kid on a swing, right? And it's going back and forth. If you push the kid like right as it hits the top, and then someone else were to push the kid right as it hits the top over here, that's how you make him swing higher and higher and higher and higher, by matching the push to be exactly when they're about to fall back down and timing it exactly so that you push at the same rate of the period. And so you increase that oscillation, okay? It's the same as jumping on a trampoline, like when you try to get your highest, and so you sort of jump right when the other person like goes to jump. So we'll talk more about these examples in class. All right, so just leave that part blank if you want to. All right, second page here. Okay, let's talk about the different types of waves that we have. Okay, so we have transverse. Okay, example for us would be light waves. Okay, and a transverse wave is a wave where looks like that. The particles that make up the wave, so the little particles that make up the wave, move perpendicular to the direction of the wave. So the wave's moving this way, right? But the particles move up and down. So this is exactly like a stadium wave. Like when you do the wave at the stadium, right? You don't get up and run down to the left or the right. You just get up and then sit back down. So you are acting as one particle of a wave that is moving around the stadium in the opposite direction, right? In the horizontal direction. So the wave moves left to right past you, but you as part of the wave just move up and then back down, okay? A longitudinal wave example would be a sound wave. Sometimes we call this a pressure wave. Okay, and these waves look like this. They have sort of, let me do a better job here. They have sort of spots where they're very compressed, and then they sort of have spots where they're more decompressed. Okay, so it's like taking a slinky and sort of pushing it. And we'll actually do this in class. I'm going to put a little note to do the slinky in class so that you remember. But essentially particles move parallel to the direction of the wave. So the particles in this piece move right and left as the wave moves to the right. Okay. And then the last type is a surface wave, and this would be like ocean waves, earthquake waves. Okay, and these waves, you basically have, they kind of look like transverse waves, but at some point they sort of buckle, right? It's like an ocean wave. And so if you had someone on a boat, right, they would be bobbing up and down. The wave would be moving this way. We're not going to worry as much about surface waves. We're more interested in these top two. Okay? All right, just to make sure you guys have these main pieces of vocab. Period. T is the amount of time for a harmonic motion to repeat itself or for the object to go one full cycle. In simple harmonic motion, T is the time it takes the object to return to its exact starting point and starting direction. Okay? So, and we measure it in seconds. And the period would be like if you had a wave, it'd be like the time between here and here. Okay? Frequency. Frequency is the number of cycles an object goes through in 1 second. So frequency is measured in hertz. 1 hertz is 1 cycle per second. So frequency is like you had a wave, and let's say we timed 1 second and we went from here to here. It'd be the number of full cycles in 1 second. Okay. And one kind of helpful and interesting equation is that frequency and the period are inverses. Okay, so these always get confused. The period is the time for 1 cycle. The frequency is the number of cycles in 1 second. Okay, so we measure this in seconds. This is measured in hertz. Okay. Amplitude is the distance from the equilibrium point to the max, or so if you were to draw kind of an equilibrium point here, the amplitude would be this distance. Okay, so from the crest to the equilibrium point. And same thing down here. Amplitude would be the crest or the trough, the bottom of the wave, to the equilibrium point. Okay. Most common mistake, people put it as the full length from crest to trough, but it's just this distance. Okay, just that short distance. Let's see what else we have here. Wave speed, we use v, the speed that a wave propagates through a medium such as water or air. So waves travel at a constant speed, which means that acceleration is 0. Okay, and sound waves, in particular, travel about 340 meters per second. Okay, so we measure it in meters per second. And still just the distance over time that it travels. Okay. Wavelength, we use this weird thing called lambda. It looks kind of like a clothes hanger. It's the distance from one crest to another crest. So it's the distance from here to here. Okay, that's one. I'm not going to put D, I'm going to put wavelength. That's one wavelength. Okay. You could also measure it from trough to trough or from one. So you could measure it from here to here. It would be the same thing. Okay. Now, finally, the wave equation is frequency times wavelength. Velocity is frequency times wavelength. And units of velocity would be meters per second. Okay. Units for frequency would be hertz. Units for lambda would be meters. Hertz is actually equal to, and we can put this up here, but hertz are actually equal to 1 over seconds. So that's how we get the meters per second here. All right, let's do a quick couple examples. All right, and then we'll do more practice during class here. A person yells in the Grand Canyon and hears their echo 1.6 seconds later. How far away is the person from the wall of the canyon? So it helps to draw a picture, okay? Here's the canyon. So they yell, okay? The wave travels to the wall and back in order for them to hear their own echo, right? So they send the waves this way, they hit off of the wall, and then they come back to the person. Okay, the time is 1.6 seconds. It's a sound wave, so we know it travels at 340 meters per second. Okay. And actually, let's go ahead and change this. It should be 343. Okay, change this to 343. Let's be more specific here. All right. And then we see how far away is the person from the wall of the canyon. So we want this distance. So the key is that you either need to cut the time in half, because the time it took to get from here to there is only half of this, because this is the time from here to there and then back to there. Or you could find the distance from there to there and back and then just divide it by 2. I would divide by 2 before, just to make sure I don't forget. So I have V equals D over T, okay, where V is 343. And then T would be half of that, so 0.8. Okay. And then if I multiply, I get 274 meters. That's how far away the wall is. Okay? Example 2, the notes produced by a violin range in frequency from, so the let's say frequency range, so F1 we'll say is 196 hertz to F2, which is 2637 hertz. Find the possible range of wavelengths in air produced by the instrument. So we want to know, lambda 1 to lambda 2, what that range is. Wavelength is lambda, okay? We know the velocity is 343 because they're sound waves. So we're going to use this wave equation. We're going to just do it twice. We're going to say, so if the frequency is 196, then lambda is 343 divided by 196. Which is 1.75. And it's in meters. And then if the frequency is 2637, then lambda would be equal to 343 divided by that, so it'd be 0.13 meters. So the range of lambda is between 0.13 and 1.75 meters. Okay? So really the only equations we have are this one. We still have this one. And then in the first page we have that one. Okay? We're going to do some examples and see some videos and stuff in class. Okay?